Assalamualaikum and very good day. I'm Dr. Hidayah from the School of Civil Engineering, Faculty of Engineering, University Technology Malaysia. First, I would like to welcome everyone to my lecture video. This video is for online learning for the course of Highway Engineering. In this video, I will discuss on flexible pavement thickness specific for the method of ATJ 5/85 revision 2013. So I hope this video will benefit you and others. So for this design method, it covers the new flexible pavements containing one or more bound layers. These bound layers refers to the asphalt mixture. And then, it also covers the new flexible for low volume roads consisting of unbound or new cement stabilized granular materials. And finally, the new flexible heavy duty pavements for severe loading conditions. So in general, pavements are usually composed of layers of different materials which have a significant impact on its performance. The composition, density and thickness of paving materials such as bituminous materials, stabilized granular materials, unbound granular road base and subbase shall be selected so that they can perform and meet the intended performance requirement. So basically the key components of a typical flexible pavement are shown in the figures. The first figure shows the single carriageway of a low volume road. Looking at the pavement layers, the design consists of subgrade, drainage layer, subbase, crushed aggregate road base, and followed by chip seal on the surface. And then on the second figure is the single carriageway for major road. Looking at the design layers, this figure consists of subgrade, drainage layer, subbase, crushed aggregate or wet mix road base, and asphaltic concrete for binder costs and wearing costs. If we compare both figures, it can be seen that the major the roads or the higher the capacity of the road, the higher the number of layers or the better the quality of the materials used. And then for the final figure shows the design of dual carriageway for major road. So in here, we can see that the road base consists of two layers made of two different materials. One is the crushed aggregate, and then another one is bituminous mixed road base, and then followed by the asphaltic concrete for binder costs and wearing costs. So what exactly the basic information needed as the input for the pavement design? So the first one is the type and volume of commercial vehicles. So remember, in all pavement thickness design, we need to consider only for commercial vehicles. And then next we have design life. So normally the design life is selected either at 10 years or 20 years. Okay, next is the subgrade type and strength. So this is very important because subgrade is like our foundation for road construction. So we have to know the strength of the subgrade. For example, if the area with low subgrade strength, of course, we need to provide with greater thickness design. Okay, next input is type and properties of paving materials. Okay, we have different types of paving materials include asphaltic concrete, crushed aggregate, stabilized material, and many more. So different type of materials will have different properties. And these properties will determine the final performance of the pavement. Okay, finally, we have another input for the pavement design, which is the environmental factor. Okay, in this design method, it considers two strains that critical in the pavement. Okay, to explain about the strains, let's have a look on the figure provided. The sketch shows to us the pavement layers and the wheel load of 40 kN. This consider half of the standard axle with two tires. The surface layer consists of bituminous wearing costs and bituminous binder costs. So at the bottom of the lowest bound layers, it is assumed that there is a horizontal strain act under tensile. The horizontal strain at the bottom of the bound layer is used to control fatigue damage due to repeated traffic load. And then we have a vertical compressive strain on the subgrade. So the vertical subgrade strain is adopted in the design to control accumulation of permanent deformation on the subgrade. In the design process, type, and coarse thickness of paving materials are selected to ensure that the above strain remain within acceptable range. So both of these strain values are expressed as a function of traffic volume. The allowable strain values decrease with the increase in traffic volume. So the strain caused by a single pass of the design wheel load must be smaller for a pavement designed for high volumes of traffic than for low traffic volumes. This is basically the outline of mechanistic pavement design procedure. Initially, we can see a few inputs. Starting with the first one is the design traffic, which consists of traffic volume, axle load spectrum, and traffic speed. And then the second input is based on material properties, which consists of subgrade strength and paving materials properties. And then the third input covers the environmental effects. These include temperature, water, and drainage condition. Next, after we have all the input properties, then we have to select reliability and structural model, calculate stresses and strain, and finally, check the predicted pavement performance against design standard. Okay, let's have a look on the detailed design procedure. First is the traffic count. This refers to the initial average daily traffic in one direction. So how to get the ADT? Normally, this data is monitored for 3 days, 24 hours per day for different vehicles type. If let's say the traffic count cover only very limited time, for example, from 6 a.m. to 10 p.m., then the count should be multiplied with 1.2. Other than ADT, we need to have traffic growth factor for the commercial vehicle. This refers to the increment in traffic, particularly for commercial vehicle every year. So by having this factor of traffic growth, we can predict the value of ADT for 10 years, for 20 years of the design. And then the second factor, we have geometric design. So for geometric design, we consider for number of lanes and terrain condition. So based on the first table in the slide, you can see the lane distribution factor is given based on number of lane per direction. For example, if you design for 2-lane highway, so the lane distribution factor is considered as 1 because it's 1 lane per direction. For the second table, it's about the selection of terrain factor. So this terrain factor is based on type of terrain, whether it's flat, rolling, mountainous or steep. Okay, next is about the selection of design period. It's either 10 years or 20 years. So when exactly we select for 10 years? Normally, 10 years is selected for low volume road, which refers to the traffic category of T1 and T2. Okay, as you can see from the table, T1 and T2 have the total axle of less than 2 million. And then 20 years is selected for the high volume road. The high volume road is referred to the traffic category of T3, T4 and T5. As you can see from the table, the total axle for T3 to T5 is more than 2 million. And then we have the calculation of the design traffic for the first year of the design period. From the slide, as you can see, the equation of the design traffic consists of few parameters. The first one is the ADT, average daily traffic of each vehicle class, multiply with the LEF, load equivalency factor of each vehicle class, and then multiply with 365 for 1 year estimation, the lane distribution factor, and finally the terrain factor, as described in the previous slide. This table shows to us the load equivalency factor for various traffic categories. As you can see from the table, the LEF for cars, taxis, and motorcycles is 0. That shows to us that this vehicle class gives less impact to the pavement surface. Therefore, this class of vehicles are not considered for the design. Others for CV1, CV2, CV3 and CV4 are considered in the design. For example, small lorries and van, large lorries and buses. However, after some time, the Public Works Department has revised this table. Let's have a look on the revised version of the LEF after several axle load study. As you know that we have so many different types of commercial vehicles, and each of them may have different axle size. That's why the value of LEF for various vehicle types must be revised regularly from time to time. So based on this new table, compared to the previous one, we have 9 categories of commercial vehicle compared to the previous table with only 4 vehicle class. So by having the revised version of LEF, this will improve the design of the pavement thickness. Okay, next we have the calculation of the total number of axle for the design period. As you can see from the slide, we have equation of easel design. So using the total of easel in year 1, we can predict for the total of whether it's 10 years or 20 years selected for the design period. So after we have the total easel predicted for the design period, and then next we need to determine the traffic category based on the value calculated. Okay, from the table provided in the slide, so it's clear that we have 5 traffic categories, T1, T2, T3, T4 and T5, based on the total number of axle predicted for the design period. And then finally you have probability, which apply to the properties of the subgrade. As I have mentioned earlier, subgrade strength is a very important factor considered in the design. So based on the table, the probability of the subgrade is proposed between 60% to 85%. So for T1, it's 60%, and T2 is considered for 70%, and for T3 to T5, the probability is proposed at 85%. In other words, we can say this probability value is like level of confidence in our design. So meaning that the higher the design traffic, the better the design, which is reflected by this probability value. So logically, of course, you need to provide better design with higher thickness or better quality materials to cater larger traffic volume. Okay, next we have a look on subgrade class. So normally for subgrade, the properties is measured based on CBR or elastic modulus. For CBR value, a minimum of 5% is considered for T1 until T3 traffic category. And if it's not achieved the minimum of 5%, at least 0.3 meter of the subgrade shall be replaced or stabilized to improve the value at least minimum of 5% before we can use this method. And then for T4 and T5, a minimum CBR value of 12% is proposed. And if it's not met, the replacement or stabilization of the subgrade need to be done. Okay, as you can see from the table provided in this slide, there are 4 subgrade categories, SG1, 2, 3 and 4. And the same category applies for the elastic modulus. So the elastic modulus is another option of measurement for the subgrade strength. Okay, so how this subgrade strength relate to the probability that I've just mentioned? Actually, the probability of the subgrade strength reflect the consistency or variability of the support or foundation. For example, in terms of the variation in soil type, density, and moisture content. That's why the following equations are provided to consider this factor in the design. So how to use these equations? Okay, later in the work example, I'll show you how to use these equations and how it's influenced the subgrade class selection for the thickness design. Okay, next is to consider the properties of the paving materials. So this method proposes the pavement to have a layer of drainage layer, sub-base course with granular material, and then road-base course made of various types of materials such as crushed aggregate, wet mix macadam, bituminous, stabilized 1 and 2. And then for the binder course, the proposed material is coarse bituminous mix, which is AC28. And then for wearing course, the proposed material can be AC10 or AC14 for the dense graded. And then PMA, polymer modified asphalt, AC10 or AC14. And then stone mastic asphalt, SMA 14 or 20. And porous asphalt, PA10 or PA14. And gap graded asphalt. Other than that, we have also thin surfacing. Normally, this thin surfacing is used for low volume road, such as micro surfacing and chip seal. Okay, what about the properties of this material? Okay, this slide shows detailed properties for the bituminous wearing and binder courses. The first table shows the detailed properties of the conventional asphalt used for wearing course and binder course. And the next table provide the detailed properties of the PMB used in the courses. These include the elastic modulus tested at 25 degrees Celsius and 35 degrees Celsius. So by knowing these values, it guides us in terms of the materials quality selected for the pavement. Okay, and then we have materials for road base. So for bituminous road base, it is treated similar to the binder course and wearing course. And if crushed aggregate is used, and then the minimum CBR value should be at 80%. Or if it's elastic modulus, and then the value should be around 350 megapascal. Okay, next is the stabilized road base. For stabilized road base, it can be categorized into two types. The first one is STB1, stabilized one, which is referred to the aggregate stabilized with cement or hydrated lime between 3 to 5%. And then STB2 or stabilized 2, which refers to the aggregates stabilized with a bituminous emulsion or foam bitumen together with cementitious material of maximum of 2% cement. Okay, next is on the environmental effects. So in the design, we did consider the first one in terms of the average climatic condition, which refers to the air temperature by considering average maximum hottest 7 days, which is approximately 38 degrees Celsius. And then in terms of the moisture, where in the design, we should prevent water from entering the pavement layers. So this can be done by providing drainage layers and use any material that is insensitive to moisture damage. So after considering all the factors and completing all the calculation of the T for traffic class and S for the subgrade strength, then we can choose the pavement thickness from the catalogue, just like what we have learned in Road Note 31. Simple, right? So the catalogue consider 3 types of pavements which give us more option to be selected for the design. The first one is the conventional flexible pavement with granular base, and then deep strength flexible, which refers to the composite that combine pavement with bituminous surface course and a base stabilized with Portland cement, or bituminous emulsion, or a combination of both. And then full depth asphalt pavement with bituminous base course. So what is the difference between these 3? The difference is based on the material selected for the road base layer. So the first one, for the conventional, it uses granular base. It's crushed aggregate material. And then for deep strength, it uses the stabilized road base. And then for the full depth, meaning that this type of pavement is made of asphalt from the surface course or wearing course, binder course until the base course or road base. Okay, let's have a look on the catalogue provided for this method. This is the catalogue for T1, refers to the traffic class that has less than 1 million easel for the design period. And then we can see here the pavement type, which consists of conventional flexible with granular base, deep strength with the stabilized base, and then finally stabilized base with surface treatment. So in this case, there is no full depth asphalt because it's low category of traffic. And then next to it, we have subgrade category from SG1, SG2, SG3, and SG4. Okay, next we have table for T2 with the traffic easel between 1 to 2 million. So based on the table, the pavement type proposed for this traffic category is the conventional flexible, deep strength, and full depth asphalt with asphalt base. As you can see, sketched in the table, the pavement thickness is given in millimeter. For example, if you need to design with traffic class of T2 and subgrade strength of SG1, if you decide to design for conventional flexible, and this will be the thickness design. And you have other option whether to use deep strength or full depth under the same category of T2 and SG1. So meaning that this catalog give us many options. It depends on what exactly the materials that we select for the pavement. Okay, next we have a table provided for T3 where the same concept applies. And then T4 for the total traffic of 10 to 30 million easel. And then T5 if it's more than 30 million easel. However, for T5 and T4, if you can see from the table, there is no proposed thickness within the category of subgrade SG1. Why? Because for higher volume road, it is not recommended to construct the pavement on top of weak subgrade. That's why the subgrade need to be improved or stabilized to achieve of minimum CBR value of more than 12%. Okay, if you can see from the slide, for T5, they provide us with two tables. So the first one is used with the conventional asphalt, and then the second table for T5 is used with polymer modified asphalt, which is better quality material. So that's why if we compare between these two, you can find that the table provided for PMA or polymer modified asphalt, the thickness used is slightly different and also the material combination. Okay, other than those tables, the method also summarize all the thickness design for the different traffic category and subgrade classes in one table. But this table focus only for conventional flexible with granular base. As you can see here, it combines from T1 until T5, and here the subgrade class from SG1 to SG4. And here you can select the combination of the thickness design. And then if you can have a look in your notes, there is another table that focus on low volume road. So how this method define the low volume road? The low volume roads is referred to the traffic category of less than 1 million. So here in this table, we have subgrade strength between 5 to 12, 12 to 20, and then more than 20%. And then next to it, we have class of the traffic. The first one, less than 100,000, and then between 100 to 500,000, and then between 500,000 to 1 million. So here you can select which one is comply with the category of the pavement under design. Okay, let's have a look on the work example. For my student, this example is provided in your notes. Okay, so here you are given a task to design full depth asphalt pavement of 4-lane freeway. So based on the HPU survey or axle load study, the result of ADT break down into different commercial vehicle from CV1 to CV9 is given in the slide. So as mentioned here, the survey was conducted only between 6 a.m. to 10 p.m. Therefore, the data of the commercial vehicle must be multiplied with 1.2 factor in order to convert the data into 24 hours period. Okay, others we have flat terrain, design life selected for 20 years, annual traffic growth rate of 4.5%, and then based on the result of subgrade testing, we've got mean modulus from HFWD or heavy falling weight deflectometer is 165 megapascal, standard deviation of 28, and reliability is 95% with normal deviate of 1.645. Okay, let's have a look on the solution. Okay, first we have to estimate easel in year 1. So looking at the equation, each of the ADT is multiplied with the load equivalency factor as given in table 4.9, and then multiply with 365 for 1 year and 0.9 for the lane distribution factor and 1 for the terrain factor. These two factors can be referred to tables 4.10 and 0.11. Then, we have to estimate the easel for the total design period, which is in this case 20 years. So, from 2 million in year 1, estimated for 20 years, it's now the easel almost 70 million for the traffic category of T5. Okay, next we move to properties of subgrade, which refers to the modulus. So using the probability equation, together with the normal deviate and standard deviation, the subgrade modulus is 119 megapascal. So using this value, the subgrade category is selected at SG3. Okay, why SG3? Looking at the table 4.13, after taking the average of the subgrade modulus compared to the mean, the average value is 142 megapascal. And then based on the table, the design input value of SG3 is the closest to 142. Therefore, SG3 is selected. Then, refer to figure 4.11 in your notes. Using T5 and SG3, select the thickness design. As referred to the catalogue and the slide, the design thickness for full deck asphalt pavement consists of 50 mm of wearing course, 200 mm of combination binder course and base course, and finally 150 mm of granular sub-base. Okay, that's all for now. Thank you very much for listening. See you in the next video. Assalamualaikum.